Hello, in this video I will do a short review on sequences and series. We will solve some basic problems, and during this I will remind you comparison about similarity at infinity, and we'll see how that works, right, in this topic. Alright, the first problem. Let's an equal to 3 to n minus 1 over 5. Let's write some terms, right? Some terms of this sequence. Okay, and then in the second question we will solve that this sequence converse or diverse. All right. So in order to write some terms of this sequence, we just plug n equal to 1, 2, 3, 4, 5, and so on, right? So what is a1? A1 is just 3, 1 minus 1 over 5. Okay, and then you get 3 to 0 over 5, which is 1 over 5. And then a2, you plug 2, 2 into the formula of an, right? So from here you get 3, 2 minus 1 over 5, which is 3 over 5. And you have a3 is 3, 3 minus 1 over 5, which is 3 square over 5, and that is 9 over 5. And then, a4, let's say that, 3, 4 minus 1 over 5 equal to 3 cubed over 5, which is 27 over 5. And similarly, you can find a5, that is 3, 5 minus 1 over 5 equal to 3 to the 4th over 5, which is 81 over 5, and so on. This is how we can write terms in a sequence if we know the general formula of the sequence, right? Okay, so I would like to remind you this, right? For each sequence, we can find corresponding function. For example, in this case, instead of n, you write x, and you get function f of x for this sequence. So that is 3x minus 1 over 5. All right, and limit of this sequence when n approaches infinity is nothing but the limit of function 3x minus 1 over 5 when x approaches infinity. So basically we need to find the horizontal asymptote of that function. Okay, so if this limit exists, if the limit function exists, so that is the limit of our sequence. All right, so let's see what is the limit of this sequence. Okay, b, let's find limit. Find limit of 3 to the n minus 1 over 5 and approaches infinity. So you can see that 1/5, that is just a number. We can take that out from the limit. We write that is 1/5 limit of 3 n minus 1 when n approaches infinity. And since 3 to n minus 1 is exponential function, when n increases to infinity, 3 to n minus 1 also increase to infinity, right? So that's why this limit is just infinity. So pretty simple, is that correct? All right, so the second question, second example on sequences. So let's consider an equal to 4 over 7 to the n plus 7. Okay, so let's find the limit of this sequence when n approaches infinity. So we have limit of 4 over 7 to the n plus 7 when n approaches infinity. We have 7 in here. That is just a number, so limit of that number is just 7, right? So basically this is equal to limit of, or let's write 7 first. So I have 7 plus limit of 4 over 7 to the n when n approaches infinity. All right, so our job is to find this limit, So we know that limit of a to the n, right? Let's say n infinity, and for a greater than 0, limit of a over n is equal to 0 if a less than 1, okay? And this limit is equal to 1 if a is 1 and equal to infinity if a greater than 1. So in this situation, a is equal to 4 over 7. That is a. So according to this, we are in the first case, right? So the limit of 4 over 7 to the n is just 0. Okay? So we have the limit of 4 over 7 to the n and approaches infinity is 0. From here, we get that our limit is just equal to 0 plus 7, which is 7. So I think this problem is not difficult. It's also easy. Okay, so we have two problems on sequences. Let's move to series. You know, on the topic of series, we have different tests. You know, we have to remind most of them. Okay, so let's consider the first problem on series. The first one look like this, where series when n from 0 to infinity of 2 over 5 to the n. All right, so you can imagine that this is geometric series, right? This is geometric series. So we know the formula of geometric series. If the number a in here, right, this is equal to a. So if the number a, I write in this form, okay? So n from 0 to infinity, a to the n, equal to 1 over 1 minus a. If a, or let's say absolute of a, so in this case a is bigger than 0, less than 1. And this is equal to infinity if a absolute greater than or equal to 1. That is the theory. That's what we know, right? And since in this situation, a is equal to 2/5, so a less than 1, okay? So this series, of course, converges, and we can find a sum by this formula. So the sum of this guy is equal to 1 over 1 minus 2 over 5, which is, 1 over 5 minus 2 over 5 in here, and then that is 5 over 3. So we are done with this problem. This is pretty easy, okay? But you have to recognize the geometric series and remember the formula, okay? Let's move to the next example. Example 4. Let's consider whether the following series converge or diverge. 7th root n to 6 n goes from 1 to infinity. All right, in this topic, we have two basic series. The first one is geometric series. That's what we did in the previous example right here, right? And the second important series is harmonic. Okay, harmonic series. How does it look? A series 1 over n to p, and from 1 to infinity. And we know that this series converges when p, or let's say for p greater than 1, and diverge for p less than or equal to 1. Okay, so our series right here looks like harmonic series, right? So how to see that? I will rewrite 7 root of n to 6. That is just, n from 1 to infinity, 1 over n to 6 over 7. So you pay attention on this, please. The power in this case is 6 over 7. So P is equal to 6 over 7, right? Then this series, converge because P is equal to 6 over 7, which is less than 1. So it's very easy. Of course, you have to remember harmonic series and value P's for which this harmonic series converge or diverge. All right, let's move to the next problem. Problem 5. We need to consider the convergence of the following series: L and n to 6, and n from 1 to infinity. All right, so see, that is also a very typical problem when you have Ln and n to 6 or to any power in here. So in this situation, we need to use comparison, between Ln x to the p, and then sometimes you need to use e to the x if they give you that. Anyway, I will remind you. So we know that Ln of n, this is very small if you compare with n to the p, right? Where p is greater than 0. Let's say that p greater than 0. And this is very small if you compare with exponential function. And this comparison happens at infinity. So that means, Ln approaches infinity slower than polynomials, and then polynomials approaches infinity slower than exponential. So how to use this comparison in this problem? I can say like this, since Ln of x is very small if you compare with n just to 1, right? So we know that Ln of n over n to the 6, of course, this guy would be greater than or equal to 0, right? But since Ln is very small if you compare with n, so that is less than or equal to n over n to the 6. I'll write here for big, enough n, from, even not for, I would say, I will write here just from big enough n. So let me remind you about this, right? This inequality might not hold, for all n, but from a big enough n, let's say from a big enough n, if this inequality holds, right, then, we can cut the finite part. So we can use comparison for the infinite part of this series. So since we have this inequality, I would write like this. I would write, 1 infinity, Ln of n is n to 6. That is, less than or equal to, in here I will write sum n over n to 6, n from 1 to infinity. In this situation, the inequality holds for any n greater than or equal to 1. Don't forget that. So I will start from n plus 1 and n plus 1. But as I mentioned previously, from a big enough n, let's say n is 0, right? So in that situation, you would write, you would replace 1 with the n0. So you can write, from n0 or n from n0. It's okay, okay? So from n0, this our series, the original series less than or equal to this guy. And this guy is nothing but, I will write here n from n0. So very general case. And then that is 1 over n to the 5th. And of course, this series converge. So, the original series greater than or equal to 0 and less than infinity. So that means our series converge. All right, this is how we can use comparison between Ln and polynomials. All right, so we already did, let's say, p-test, geometric series, okay, and comparisons. And now let's use ratio test. The next problem looks like this. We need to consider whether this series converges or diverges. So first thing, when you see something like that, of course you need to we need to recognize AN, right? So what is AN? AN in this case is just, product of the first n odd number, okay? And in here I have product of first and even numbers. So that is our sequence. And now let's look at this. So see, on the top you have 1, right? And right here you have 2. In here you have 3, and here you have 4. So, each time when you move to a next step, you just increase your number on 1 unit, right? In the denominator. So you have 1, 2, 3, 4, and then 5 to 7 in here. And then so on, 2n minus 1, 2 to 2n. So you would think like this. Yeah, maybe, the top and the bottom, they have the same degree. So, that means this series diverse, because if they have the same degree, means this guy is almost the same with 1, right? Not exactly 1, of course that is less than 1, but I mean, if you use comparison, yeah, it's some kind of similar to 1. And sum of 1s is infinity, means diverse. So you might think that, yeah, this series is diverse. All right, so how to prove this? We need to use comparison, right? If we think like this series diverse, we need to show that this series is greater than some series that diverse. Okay, so say here's comparison, right? So if you have some an and you think, yeah, if you want to show that an diverse, right? So you may you might need to prove that you compare an, which is greater than or equal to some bn, which is converging, okay? Which no diverging, right? So in this situation, an looks like this. So how to find bn? So I'll find bn in the following way. Let's say I will rewrite an, okay? An is 1, but 1 is nothing. 1 is 1, so I don't write it because the product 1 does not affect on my product. I write 3 over 2 times 5 over 4 times so on times 2n minus 1 over 2n minus 2 and times 1 over 2n. Okay, you see, I just, rearrange the quotient a little bit. So here, instead of 1, 1, I write in here, okay? So I have that. And let's pay attention on each factor in here, right? So this guy is greater than or equal to 1, this guy is greater than or equal to 1, and so on. This guy also greater than or equal to 1. So overall, an is greater than or equal to 1 over 2, and in here, right? And we know that, from here I have sum an, and from 1 to infinity greater than or equal to sum of 2n in here, and from 1 to infinity, and that is nothing but 1 over 2, because 1 over 2 is number, we can take that out, and from 1 to infinity 1 over n, and this is harmonic series, right? This is a harmonic series, and this series diverse, right? Because the power p is equal to 1. So since this series diverse, this series also diverse and equal to infinity. All right? Yeah, this problem is interesting. I will tell you this. This interesting, and from the point of view that the definition of an. If we look at an again, right? So an is defined recursively. Let's say an is defined recursively, right? Why? Because when you write an plus 1, and you can express an plus 1 VAN, so that is a problem. That can make us confused. So I write here 1 times 3 times 5 and so on, and 2n minus 1. And then since I have n plus 1 in here, so I have 2n plus 1 minus 1 over 2 times 4 times 7 times so on times 2n, and then times 2n plus 1. Okay, so if you practice like into 1 times 3 times 5 and so on, 2n minus 1, divide by 2 times 4 times 7 times 2n, right? And then in here 2n plus 1 over 2n plus 2. Okay, why do we have that? Because 2n plus 1 comes from here, okay? Comes from here. Because you open parentheses, 2n plus 2 minus 1, which is 2n plus 1. You do the same thing for 2n plus 1. So you open parentheses, you get 2n plus 2. Okay? So basically, what is this? What is this? That is your an, right? So that means, an plus 1 is equal to an times 2n plus 1 over 2n plus 2. Unfortunately, we cannot use ratio test in this situation. Why? Because the ratio of an plus 1 over an has limit equal to 1. We cannot use ratio test because limit of an plus 1 over an when n approaches infinity is equal to limit of 2n plus 1 over 2n plus 2 when n approaches infinity, and this limit is obviously equal to 1. You see? So, when the ratio has limit equal to 1, we cannot do any decision. So, I mentioned this because sometimes when you try to apply a ratio test or a root test and you get limit equal to 1, so let's change the strategy. Okay, all right, let's move to the next problem. So the next problem is about the alternating series test. Suppose that we have the following series: sum n from 2 to infinity, -1 to n. In here we have n over n squared minus 2. So this is alternating series, right? And in this course, if you see some alternating series, so we need to use alternating series test. Of course, I will not give you a series like diverging series, right? Diverging alternating series. So that's not my purpose. So you have this. Let's use alternating series test. So what does alternating series test say? So if you have something like this, right, or in general, -1 to n and then an, and from 1 or 2, no problem. When n an greater than or equal to 0, let's say greater than 0. If you have something like that, and you see, an is decreasing, and the limit of an is equal to 0. So we have two conditions in here. If an satisfies, these three conditions, we do conclusion that our series converges. Okay. All right. So let's say how to prove that an is decreasing. So we have two ways to prove an is decreasing. Let's talk about this first. Okay. So an is decreasing. You may prove that the function, the corresponding function for an is a decreasing function. So in this situation, I have f of x is equal to x over x squared minus 2. So that comes from here, okay? Here's x squared. So that's why I have x in here and then x squared minus 2 in here. we can prove that this function is decreasing, which is equivalent to that, the derivative of this function is negative from a big enough x. Okay. Again, we just care about big enough x. So I can write, let's find the derivative of this function. The derivative of this guy is equal to, we use the quotient rule, say x derivative times x squared minus 2 minus x squared minus 2 derivative times x over x squared minus 2 squared, right? That is quotient rule. X derivative is 1, so I have x squared minus 2 in here, and this guy derivative is 2x times x, right? Over x squared minus 2 squared, and then we can simplify this. We get, negative x squared minus 2 over x squared minus 2 squared. So the part right here on the top is always negative, and the denominator is always positive. So that means this guy is always negative, right? For let's say for x greater than 2, that's okay. So since the derivative is negative, that means an is decreasing because the function is decreasing. So we prove the first condition, right? Now let's check if limit of this an is 0 or not. Okay, let's say the second one. Let's check the limit of an approaching infinity. That is equal to the limit of n over n squared minus 2 when n approaches infinity. Of course, this limit is 0 because you can say, you can use similarity at infinity. On the top you have n, in the bottom you have n squared, right? N approaches infinity, and this is just limit of 1 over n approaches infinity, and that is 0. So we are done, right? We already checked the second condition right here. So this series satisfies these two conditions. So by alternating series test, the series converges. Series test, the series converges. Okay. So we are done with this problem. All right. Let's move to power series. Okay. Power series. So here's the general formula of power series. That is, an, and then x minus c to the n, and from 0 to infinity. And let's remind you about c. C is called central. Okay. And of course, an is coefficient. When we consider power series, we have to find the interval of convergence. We have to find the interval of convergence. And since we consider central C, right? So your interval of convergence should be symmetric with respect to the C. Don't forget about that. All right. So when we find interval of convergence, we are good. We can do that, using, let's say, a ratio test or a root test. Okay, root test. Let me remind you about ratio test and root test, and then we move ahead. Just go ahead to solve one example. So ratio test look like this. You have to find R, which is the limit of an plus 1 over an. Okay, and approach is infinity. And once you found R, you can set this guy less than 1, because we know that when R less than 1, our series converges, right? And similarly, you can do root test. You find R equal to limit of n root of absolute an and approach infinity, and you set this equal to less than 1. And then after this two, after this situation, you still need, let me write here, we still need to consider two endpoints. Okay, let's consider the following example, and then we'll see how that works. Let's consider series 7 to the n, and then n minus 1 to the n. Sorry, here I have x minus 1, and n go from 1 to infinity. All right, so look at this. In this situation, our an looks like 7 to n, x minus 1 to n over n, right? So, from the definition of an, we need to decide ratio test or root test would work, right? So in this case, I would say, yeah, I would apply ratio test. Why? Why we don't apply, root test? Because if we apply a root test, we would have the following. Okay, let's say an, right, absolute, to n. For 7 to n, I'm good with this, right? 7 to the n. And then x minus 1, absolute, to the n, with the root test ending here. And I have root test, n root of n. So on the top, I have 7 times absolute of x minus 1. But in the bottom, we have n root of n. We are good with the top because, it does not depend on n. But how to find the limit of this guy? Of course, this is solvable, but, it's too complicated. So I would use the ratio test, right? Okay, in order to use the ratio test, okay, I write here ratio test. If you don't get that from the beginning, you might try both, okay, and then choose the suitable one for you. So the ratio test, for that you need to find an plus 1. Okay, so right here, instead of n, you have n plus 1, you have 7 to n plus 1, and then you have x minus 1 to n plus 1. That comes from definition, okay? So instead of n, you just plug n plus 1. So in here, in the denominator, I have n plus 1. I divide this by n. I get 7 plus 1, x minus 1 to n plus 1 over n plus 1. Divide. So you divide by an, right? But your an looks like this. So you flip that, you multiply by the inverse, okay? So I write here, okay, anyway, I write divide by 7 to the n, x minus 1 to the n over n, right? So we flip that, we get 7 to n plus 1, x minus 1 to n plus 1 over n plus 1, multiply with the n over 7 to the n, and then x minus 1 to the n, right? All right, now let's simplify it. Here I have 7 to the n. I here have 7 to the n plus 1. But 7 to the n plus 1 is just 7 to the n times 7. So we can simplify 7 to the n, right? On the top, I still have 7 because I already cancel 7 to the n here. Again, another one is x minus 1 to n plus 1. Here I have x minus 1 to n. I do the same thing. I have x minus 1 to n plus 1 equal to x minus 1 to the n times x minus 1. And then I simplify x minus 1 to the n, right? So on the top, I have x minus 1 in here, and then n over n plus 1. Because n is right here, we come here, and then n plus 1, we come down here. All right, from here, I will take absolute, and I consider a limit of absolute of an plus 1 over an. Okay, when n approaches infinity, so that is 7 absolute of x minus 1, because that is just a number. We can take that out of limit, okay? And here I have limit of n over n plus 1. All right, so we know this limit is just 1, right? Because on the top you have n, in the bottom you have n plus 1. So this limit is equal to 7 absolute of x minus 1. All right, so as we said previously, we need to set this less than 1. Where's that? This guy, less than 1. Okay, we need to set this less than 1, and then we solve for x. All right, so I will set this guy, less than 1. So since this guy less than 1, I have absolute of x minus 1 less than 1 over 7. And then this is equivalent to that, x minus 1 less than 1 over 7, and then greater than negative 1 over 7. So we add 1 to 3 sides, we get x less than 1 over 7 plus 1, and greater than negative 1 over 7 plus 1. So x less than 8 over 7, greater than 6 over 7. So that is, the interval we found without endpoints. Okay, so we still need to consider, our series at 2 endpoints, because, sometimes when you plug 2 endpoints into the original series, our series converse or sometimes diverse. Okay, so let's consider to add 2 endpoints. Say at x equal to 6 over 7. I have to plug this guy into the original series. Okay, what is the original series? Let me remind that. That is series from 1 to infinity, 7 to the n, and then x minus 1 to the n over n, right? So when you plug 6 over 7 into this guy, this series just equal to series from 1 to infinity, 7 to the n, 6 over 7 minus 1 to the n over n, right? Let's simplify this. This is equal to sum n from 1 to infinity, 7 to the n. 6 over 7 minus 1 is negative 1 over 7 to the n. In here, you have n. All right, so let's simplify this series, right? And we'll see. n from 1 to infinity, 7 to the n. Another factor can be written as negative 1 to the n, and then divide by 7 to the n, everything divided by n. So you have 7 to the n in here, 7 to the n in here. You can cancel them out, and you get n from 1 to infinity, negative 1 to the n over n. And this is alternating series, right? This alternating series. And what is an? An in this case 1 over n. And we know that an decreasing. Okay, and the limit of an is 0, is obvious. So by alternating series test, this series converges. Okay, this series converges. Okay, I write here converges. So that means when x equal to 6 over 7, our series converges. Means this point should be in the interval of convergence. All right, now let's consider another endpoint. Okay, when x equal to 8 over 7. Again, you plug this point. You plug this point into the series, into the original series. So our series look like this. Okay, let me see the series. So the series sum 7 to the n, 8 over 7 minus 1 to the n over n, and from 1 to infinity. We do a computation and we simplify them. And from 1 to infinity, 7 to the n. 8 over 7 minus 1 is 1 over 7 to the n over n. So of course you see here we have 7 to the n, 1 over 7 to the n, and 7 to the n. That is just 1, right? So basically this is equal to sum from 1 to infinity 1 over n. And this is harmonic series. The power is 1. So this series diverges. That means another endpoint is not in the interval of convergence. So from here we can do conclusion. Now the interval, the series converge on 6 over 7 to 8 over 7, but 8 over 7 is not included. So see, this problem is pretty long, right? So we have to apply all techniques, basically all techniques in this topic, and including alternating series. Okay,